Okay, so we are ready to draw a very rough sketch of our solution curve. So I've recorded the basic information here. The period of a single beat is 16 pi, and actually with the beat, I am more concerned about the period than the frequency, although they go hand in hand. We determined that there are going to be 15 rapid oscillations per beat, and we determined that the amplitude was going to be the sum of the amplitudes of the natural response and the forced response. Now, if you remember, when we solved for A and B for our particular initial condition, A was the opposite of this number right here, and B was just 0. So, basically, when I square the opposite of this, and then take the square root, I just get a second copy of that. So we're getting 2 over 16 minus 3.5 squared. That's approximately 0.53. I will confess I plugged that into a calculator. Okay. Now, I had to choose something that was close to 4, which meant I was introducing fractions, so the numbers were a little bit messy. I would be totally fine on a quiz or an exam with you just leaving things in this form. Okay. Actually, yeah. On a quiz, you could get a decimal approximation, but label it exactly. But I'm not going to expect you to simplify that. That's just tedious arithmetic. That's a good place to go ahead and use a calculator. Okay. So, I'm going to draw my beats. So the period is 16 pi. So when I'm drawing one sine or cosine curve, I usually break it up into 4 pieces. So we'll have 4 pi, 8 pi, 12 pi, 16 pi. I'm going to just say that this is, let's call it A for amplitude. So that's A and negative A. And I'm going to just mark off, starting at 0, going to a high, middle, low, middle. I'm going to draw a dotted curve that defines the beats. And then I'm going to draw the opposite of that, and that's the little shell in which I have my rapid oscillations. Now, this is one beat, okay? Almost looks like 2, but remember, if I look at one of these functions, its period was 16 pi. Okay. So now it's time to draw the rapid oscillations, and I have to have 15 of them that I fit in here. So that's going to be 7.5 in each of these half beats. Now, I am going to start at 0 because remember we said that our initial condition was that we were at 0. We also said our initial condition was that the first derivative was 0. So that's going to mean we're either at a high point or a low point. Now, I'm not concerned that you get this exactly to scale, but I'm going to just suppose I'm at a high point here. I'm just going to make a choice. I could, if I really wanted to, I could plug in some numbers and figure it out. But I'm going to now try to say I'm at a high point here, and I want to get in 7.5 beats. So, rapid oscillations. So if I start at a high point, that's one oscillation. Half of an oscillation would be at a low point. So if I'm at a high point here, this is going to be a low point here. Okay. So let's see. 1, 2, 3, 4, 5, 6, 7.5. That's now a low point. 1, 2, 3, 4, 5, 6, 7.5. My curve's going to look something like that. I'm most concerned that you can get these numbers correct and draw me a very rough sketch. I'm not concerned that you get your sketch exactly perfect. Okay. But that's how we would sketch a representative solution curve. And yes, what we get will vary depending on the initial condition, because that's going to affect what A and B are. So we won't necessarily, for all solution curves, necessarily be starting at the origin. We just chose that because it's a really nice initial condition for being able to figure this out. But the period of the beats and the number of rapid oscillations per beat, we can always calculate this way using these numbers alpha and beta. Okay. So this example took 3 videos, okay, because we were doing a lot of theory in with the examples. Next video, we're just going to do an example, just plug through the computations.